Chemical properties. Like the alkenes are very flammable and undergo combustion. Any hydrocarbon that undergoes combustion gives carbon dioxide and water as the products. So that's the same as for the alkanes. The alkenes though also undergo some other reactions. They are much more reactive than the alkanes. So we have addition reactions. An addition reaction is where we're adding something to the molecule. And the thing that is being added adds at the functional group, which is the double bond. So addition reactions are where you have atoms or groups of atoms being added to each carbon of a double bond. And we tend to say that it's adding across the double bond. This can be symmetrical or unsymmetrical. In a symmetrical addition, we have the same thing being added to each side. In an unsymmetrical addition reaction, we have different things being added to each side of that double bond. So here's a picture. So here we have ethene. We've got 2 carbons with the double bond. And here we have a molecule coming in, and this is going to add to this double bond. This is going to be unsymmetrical because this molecule has 2 different atoms. And so the yellow one is adding to this side and the purple one is adding to that side. There's 2 different things being added. If these were both yellow or both purple, it would be symmetrical. And what you end up with is that this thing being added takes the place of the double bond. So this carbon atom still has 1, 2, 3, 4 bonds. And this carbon atom has 1, 2, 3, 4 bonds because carbon always makes 4 bonds. Over here it also had 4 bonds, but 2 of them were with the same carbon atom. It had a double bond. So we essentially break one of these double bonds and form a bond with these new things. That's an addition reaction. And there's some different types of addition reactions, but they all have the same general idea. So there's 2 main types of symmetrical reactions that we'll talk about. One is hydrogenation. This is where you're adding hydrogen. Okay, and these names give you a clue. Hydrogenation, adding hydrogen. So the hydrogen is added. So here we've got 2 propene. The hydrogen is going to add across this double bond. So we can imagine the hydrogen coming in here, and I imagine it kind of coming in here and is landing like a spaceship or something, and then this double bond breaks, and we form a bond between this hydrogen and this carbon, and this hydrogen and that carbon. It's symmetrical because each carbon in the bond is getting the same thing. And so we end up with propane because we've now lost the bond, the double bond. So this is just all single bonds. Propene becomes propane. So we've turned it into an alkane. This doesn't happen spontaneously. It usually requires heating and a catalyst. A common catalyst is nickel or platinum. When we write the equation here, we're going to write any conditions that are needed above and below the arrow. So if it puts Ni here or Pt, that is not a reactant, it's a catalyst. And if you remember from Chem 3A, a catalyst is something that speeds up the rate of the reaction. It doesn't actually get consumed in the reaction. My analogy for that is it's a little bit like the reaction is kindergartners climbing over this fence. Okay, and they're getting over the fence, but they're getting over it very slowly. A catalyst would be a teacher standing at the fence and lifting them up over the fence. They're going to get over faster now. One teacher can catalyze many children going over the fence. So it just makes it faster. Yeah, I don't know what else to say about that one. A halogenation reaction is also a symmetrical addition reaction. And here we're adding a halogen. Okay, halogens, if you remember, are diatomic elements. So chlorine, bromine, and iodine are the common ones we see in organic chemistry. It's Cl2. You don't have chlorine atoms just floating around. You have these chlorine molecules. And so this chlorine molecule, just like the hydrogen, comes and attaches across this double bond. So one chlorine goes to one carbon and the other chlorine goes to the other. This is symmetrical because they are each getting the same thing. And so what we end up with here is 2,3-dichlorobutane. So this was 2-butene. The chlorines are adding across that double bond, so we get one on the second carbon, one on the third carbon. Now it's not butene anymore because the double bond's gone. It's butane, 2,3-dichlorobutane. This doesn't need a catalyst. This goes pretty well on its own. Any questions? You can also have an unsymmetrical addition reaction. So this one is called hydrohalogenation. So this is where we've got something like hydrogen chloride. See, there's hydrogen and a halogen. So hydrogen chloride, hydrogen bromide, hydrogen fluoride, adding across the double bond. So one side gets hydrogen, the other side gets chlorine. Not the same, unsymmetrical. Okay, so halogenation is adding a halogen, hydrogenation is adding a hydrogen molecule, and hydrohalogenation is adding a hydrogen halide. Another type of unsymmetrical reaction is hydration. What does hydration make you think of? Water. If you're dehydrated, you don't have enough water. If you're hydrating yourself, you're drinking a lot of water to get enough water into your body. So hydration is adding water. Well, we think of that as the H is going to go to one side and the rest of it, the OH, is going to go to the other side. So this is unsymmetrical also. One carbon gets the hydrogen and one carbon gets the rest of it, the OH. And so we end up with the product being an alcohol. When it has this OH group on it, that makes it an alcohol. And we're going to talk about those in Chapter 3. This also requires a catalyst of sulfuric acid. Let's look at this example. So here for propene, adding HCl, what kind of an addition reaction is this? Hydrohalogenation, because of what we're adding. So there's two different possibilities here. We can have this guy coming in like this, and the chlorine going on the first carbon, giving us this product, or it could come in this way, and we'll end up with the chlorine on the middle carbon. So there's two different things that could happen. They don't happen in equal amounts. When you do this reaction, one of them is preferred over the other. And we're not going to get into predicting how much, but we have this general guideline called Markovnikov's rule. Markovnikov was a Russian scientist who figured this out. And basically what this says is when you have an unsymmetrical molecule, HQ, so it could be HOH, water, or it could be HI or HBr, anything asymmetrical with a hydrogen on it. When that adds across, the hydrogen is going to prefer to go to the carbon that has more hydrogens. So if we look at these two carbons, this one has one hydrogen and this one has two. This hydrogen is going to prefer to go to this one. This is the reaction that's going to be preferred. And one way to state Markovnikov's rule is the rich get richer. The rich get richer. It's not money, but hydrogens. This carbon has one hydrogen. This carbon has two hydrogens. He's richer. He's got two hydrogens. We're going to end up with this being preferred, with this carbon getting richer and this guy not. Another way to think of it is, think about people emigrating to the United States. Let's, I don't know, pick on the Swedes because I'm Swedish. So the Swedes, were emigrating to the United States, and like many ethnic groups, they end up clumping up in different parts of the United States. Because if you're going to a strange country and you're choosing between a city where there's a bunch of Swedes and a city where there's no Swedes, and everything else is the same to you, you don't know where you're going, you're going to go to the city that has more people like you, right? It's just going to be more comfortable. They're going to speak your language, they're going to be able to help you out, and you're just going to feel more comfortable. So that's how I think of the hydrogens here. The hydrogen, the hydrogen chloride is coming in here, and the hydrogen's looking around saying, I could go here, I could go there. Hey, I'm going to go over here because I've already got two buddies, two hydrogens there. So that's Markovnikov's rule. So there's not always two different isomers that can be formed, but many times there are. So here we have two different possible products, one chloropropane and two chloropropane, and we should be able to identify which one there will be more of. It's not going to be 50% and 50%. There's going to be more of this one because of what Markovnikov's rule says. Any questions? So let's practice. Predict the predominant product in each of the following addition reactions. So in A, we're adding HCl, and the HCl is going to add across the double bond. And so this hydrogen is going to look and is choosing between these two carbons. Which one is it going to prefer? The first one, because there's already two hydrogens here. The hydrogen is going to go to the side with more hydrogens. So then our product here, we're going to get rid of that double bond, and the rest of it's all going to stay the same. And the hydrogen is going to go over here, and the chlorine is going to go over there. That's the predominant product. Let's name that guy. What's his name? 4 carbons, so it's what? Butane? And we're going to say that the chlorine is on number 2 or number 3? Number 2, right? This is 1, 2, 3, 4, or 1, 2, 3, 4. So 2-chlorobutane. That's supposed to run together. And what was this guy named? The first guy, the reactant. Also 4 carbons, right? But it's got a double bond. So it's not butane. Butene. Do we have to specify where that double bond is? We do, because it could be on the end like it is, or it could be in the middle. So there's 1 butene and 2 butene. This is 1 butene. Let's look at letter B. Some of these line angle drawings just look like weird geometric shapes. So adding HBr, the HBr is going to add across this double bond. So the hydrogen's choosing to go here or to here. Which one of those carbons has more hydrogens? None of the hydrogens are shown, are they? The bottom one has more hydrogens. Because if we look at this guy, he's got 1, 2, 3 bonds with carbons. There's got to be a hydrogen over here. This guy has 1, 2, 3, 4 bonds with carbons. That guy has no hydrogens. So the hydrogen is going to go this way. So if you're doing a true line angle, you're not going to show any of the hydrogens. And it may be helpful to you to actually, show some of the hydrogens like I did over here. And so then over here, you might show hydrogens like this, and then recopy that without the hydrogens. Now, what would the name of that guy be? Four carbons, right, in the ring would be cyclobutane. And we got 2 substituents on that, right? This up here is methyl, and this is bromo. Which one comes first? Bromo. And they're both on the same carbon, aren't they? We'd want to call that carbon number 1. So that'd be 1 bromo, 1 methyl, cyclobutane. Just for
hey, why did you leave the chlorine out of the name?
Why did I leave the chlorine out of what?
Out of the name? Get 1-butene.
Oh, this doesn't have any chlorine in it. This is the reactant. It's reacting with HCl. I was just drawing this guy above, showing as he's coming into land. He hasn't landed yet.
So the chlorine doesn't go in the product?
The chlorine's right here in the product.
Oh, okay. Good.
Yeah,
Over there.
it's
Okay.
hiding.
Oh, I see what you're showing it. Okay.
Yeah, there's lots of different ways to show things, which makes it confusing. And if it makes you feel any better, it also makes it very difficult to grade things that are written out. So let's clean that up and just name this guy. What would that guy be? Let's think of him first without the methyl group. Cyclobutene, right? Do we need a number for that double bond? No. There's only one double bond. We're always going to start numbering 1 on the double bond. And it's got a methyl group on it, right? And what carbon is the methyl group on? The 1. So this is 1 methyl cyclobutene. Two more examples. Oh. What? I thought there was an A, B, C, D. There's not. Okay. Different example. Supply the structural formula of the missing substance in each of the following addition reactions. So this is fill in the missing piece. So whether it's a question mark, what is that? So what do we have going on up here? Here we have an alkene, and we're adding HBr. So this is a hydrohalogenation reaction. This HBr is going to add across this double bond. This carbon has 1 hydrogen. This carbon has 2 hydrogens. So the hydrogen is going to want to go to this side. So I'm going to just draw it in above. And I picture it coming in and landing. Okay. I have lots of weird pictures in my head. So CH3, CH2. Here's that double bond. I'm just going to draw a single bond because the double bond is going to be gone. And the hydrogen is going to attach to that one, and the bromine is going to attach to this one. Because Markovnikov's rule tells us that it'll go that way. Now, will some of the other isomer form? Yeah, but this is the majority, and that's all we're going to worry about. How about this one on the bottom? What do we have going on here? Adding water, what kind of a reaction is that? Hydration. The water adds across the double bond. So the hydrogen adds to one side and the OH adds to the other side. Here they're giving us the product and not the reactant. We can look at this product and see, oh, well, there's the OH. That must have been one side of the double bond, and over here must have been the other side. So now I'm going to, draw a picture of it taking off. So this is taking off. This OH came from the water that was put in there, and the hydrogen on here came from the water that was put in there. If I take those off, then I get a double bond there. And so what this started out as was something like this. Because it's kind of working backwards. It's like saying, what plus 5 equals 7? Right? So you have to look at what the difference is. Because if we take this guy and we add HOH to him, we're going to get the other guy. So what's the name of this one? Well, what's the longest chain? Over here, this guy. That's cyclopentane, right? And we've got this guy attached to it. That was a CH2 with a double bond to that cyclopentane ring. Do you know what the name of that guy is? We talked about it earlier this afternoon. That's an alkenyl group. It's methylene. So this is methylene. Methylene cyclopentane. Any questions? Let's look at this one. Here we've got a cyclodiene. It's got 2 double bonds. And 2 somethings are being added to it with a nickel catalyst. And we're ending up with this cyclohexane, no double bonds. Now it doesn't look like there's any substituents on here, does there? What could we add that would do that? It may help to draw the condensed structural formula. This guy had a CH2 and a CH2 down here. What about this carbon? How many hydrogens did it have? Only 1, right? Because it's got 2 bonds here and 1 bond here. So there's 1 implicit hydrogen on that guy. And there's one implicit hydrogen. Because each carbon has to have 4 bonds. 4 bonds. So what's the difference between these two structures? What's missing in this one that is present in the product? Hydrogens. So what got added across the double bond? Hydrogen, right? H2. So here the question mark is H2. So we had a hydrogen adding across that double bond and a hydrogen adding across this double bond. Comes in, removes the double bond, and it's got, now this is a saturated cyclohexane. How about this guy at the bottom? What's going to happen here? So that was a hydrogenation reaction for letter C. Letter D is what type of reaction? Halogenation, adding a halogen, chlorine. The chlorine's going to add across the double bond. One chlorine goes to one of those carbons. So this one will go to this carbon, that one will go to that carbon. We don't need to consider Markovnikov's rule because this is a symmetrical addition. The same thing is being added to both sides. So I can just copy this guy down without drawing the double bond. And where the double bond was, I'm going to put those chlorines in. Now, could you draw that product a different way? Yeah, I mean, there's lots and lots of different ways you could draw that same product. But why make things harder than they are, right? So I think it's simplest to just draw it the same way, but we're removing one of those double bonds, and we're attaching a chlorine to each of the carbons that had the double bond.
And that CH2CH3.
Yes, thank you. I missed the 3 there. Good catch. Okay. I remember taking organic chemistry. I had to take the 2-semester sequence and just hating all the reactions that I had to memorize. It's much easier to remember the reactions if you remember them as categories. So an addition reaction, you've got something that's adding across the double, or we'll see later, we can also add across the triple bond. The description tells us what's being added. Hydration, we're adding water. Halogenation, we're adding a halogen. Hydrohalogenation, we're adding a hydrogen halide. One part of it goes on one side of the double bond, one goes on the other. I am not going to grill you on catalysts. The catalysts will show up, but I'm not going to, say, well, what do you need a catalyst for hydrohalogenation, and if so, which one? I don't think that's that important. Okay, you'll see them in here. They'll always be written in there when they need to be there, but I'm not going to specifically test you on what catalyst it needs or if it needs a catalyst.